All right, and it's possible we won't actually go the whole time today. We'll see. So I just want to get you up to the point where you can do the homework, but I've pre-written a bunch of code if you happen to see it on Slack. But in any case, we're going to remind ourselves how MergeSort works, because that's Jason's favorite.
We're doing it in another class too at the same time.
Which class?
The same thing in theoretical.
But are you going to write that with multiple processes? It's gonna be.
It
It is kind of funny. I think Blade probably did MergeSort with me five different classes probably at some point in time. You know, it's a really good algorithm to keep coming back to because you can look at it from a bunch of different angles, and that's what we're going to do in here is kind of start seeing how MergeSort is good. All right. So just as a reminder, I want to go through and visually remind ourselves how MergeSort works. Then we'll look at the algorithm for MergeSort, and then we're going to talk about what are some multi-process possible solutions to solving MergeSort, and then that'll be your homework assignment is to actually solve it. Okay. Just go after this. All right, so if you remember, MergeSort takes a list of elements, and I'm going to keep it relatively short. We'll just do it based on 5 things here. So let's say this is a 3, a 1, a 7, 2, 8, something like that. So, and these are array indexes. All right, so the idea with MergeSort is it's a divide and conquer algorithm, which is probably the angle you're talking about it from in 490. Is looking at different algorithms. So this happens to be a divide and conquer kind of algorithm. So the idea here is we ask the question, is this data sorted? And MergeSort operates on this premise of whether something is trivially sorted. So something being trivially sorted means it's a list of exactly one thing. So if we're looking at the entire list, we say, no, that's not sorted because it's not a 1 list. So if it's not a 1 list, what do? Well, we divide it in half. We divide it into the left half, and then we divide it into the right half. So this is our first recursive call to MergeSort. This is our second recursive call to MergeSort, but this guy won't happen until all the left-hand side occurs first. All right, so we're in our first recursive call here. We ask ourselves, is that guy trivially sorted? It's not. Why? It's not a 1 list. So what do? We divide it in half. We divide it in half, so we have 2 calls to MergeSort. So now we're on the first call off of this call to it. We say, is this trivially sorted? No, it's not a 1 list. So what do? We divide it in half. We divide it in half. The first call to MergeSort, we say, is that guy trivially sorted? It is. It's only a 1 list. So what do? We do nothing. It's already sorted. Return. Then we get to our second call to MergeSort. Is that guy trivially sorted? He is. It's a 1 list. So we return from that call. So now we're sitting at this portion of the list. And at this point, we do our merge step. So after our 2 calls to merge sort, we're going to do our merge step where we create a temporary array of the same size as our as the portion of the array that we're currently focused on. And we go through and we ask the question. So we're comparing all the elements in the first half, which are sorted in and of themselves, because we know that this one list is sorted, and all the elements in the right half, which are sorted in and of themselves, because we know that right half is already sorted. And we say, who is the smaller value, the 3 or the 1? We pick the winner as the 1. Then we say, who is the smaller value, the 3 or an illegal position? By default, the 3 wins. So we place the 3. Then we know we're done because we were off the end of the first half and we're off the end of the second half. So we've placed all the numbers we need to place. Then we copy our values back over, because remember, this is actually in memory. We're passing pointers around. So we copy the 1 here, the 3 here, which will have a side effect throughout memory, all the places that point to that. And then this call to merge sort X. All right, so this guy has already made his 2 calls to merge sort and he's done the merge step. So this first part of this guy is already sorted in and of itself. Then, so this guy ends. We get to our second call to merge sort at this level, which is this one list. Is this guy trivially sorted? Yes, he is. So this guy's done. So now what do? We do our merge step. Create a temporary array of the same size as the portion of the array we're currently looking at. And we have a counter that looks at the stuff in the first half and a counter that looks at the stuff in the second half. We say, which is smaller, the 1 or the 7? The 1. Which is smaller, the 3 or the 7? The 3. Which is smaller, the 7 or an illegal position? The 7. We've placed all of our stuff in there. It happens to already be in order, but we would overwrite. We put the 1 over this guy, the 3 over this guy, the 7 over this guy, which will then have an impact, long-term impact, even though we didn't change anything at that level. So now this call has completed. So we see that the first half of our array is already sorted in and of itself. Now we get back to our original second merge sort call. We say, is this guy trivially sorted? No. So we call merge sort on the left half. We call merge sort on the right half. Is this guy trivially sorted? Yes, it is, because it's a 1 list. Is this guy trivially sorted? Our second call there? Yes, it is. It's a 1 list. So now we create our temporary array that's of the same size as the portion of the array that we're dealing with here. Now, this is where the algorithm for merge sort can be a little bit tricky, because actually my temporary array, this is bucket 0, bucket 1. But the original array, I'm actually looking at bucket 3 and bucket 4. I'm looking at a different portion of the original array, but I'm copying it over to this temporary array. That array is this array of size 2, has indexes 0 and 1. All right, so this is where you need to be a little careful in the algorithm. It's not necessarily hard, just it's error prone here. And I'll point that out when we go into the C algorithm for this. All right, so we ask, which one's smaller, the 2 or the 8? The 2. Which one's smaller, the 8 or an illegal position? The 8. Copy that over. Nothing's actually changed, but we would have copied it over. So now the original second call to merge sort has completed. So now the left half is sorted in and of itself. The right half is sorted in and of itself. We create a temporary array of the same size. We ask ourselves, which should come first, a 1 or a 2? the 1. Which should come first, a 3 or a 2? Go ahead.
Why is it 1 versus?
Because it's the bucket 0 of the first half versus bucket 0 of the second half. So we placed the 1 already. So now it's 3 competing against 2. The 2 wins. So now it's 3 competing against 8. The 3 wins. So now it's 7 competing against 8. The 7 wins. So now it's in a legal position competing against 8. Because we're off the end of the first half. The 8 wins. We've placed everything. Copy it over. So 2, 3, 7, 8. And now our data is sorted. All right. Make some sense? All right. So now let's go and look at the code equivalent of that. Walk through, make sure everybody understands what's going on. I'm going to point out a couple of C-related highlights as we do it. And then we're going to come back and talk about why MergeSort is good and how can we, well, why MergeSort pretends to be good, but actually isn't good recursively, but actually is good when we think about it in terms of multiple processes. All right, which is how it relates to this class. So let's go and look at the code here. And we're going to programmatically say the exact same thing we just said. Okay. So I've included a couple of things because actually I initialized my array with some random numbers. I don't remember if we've done random numbers in here yet. So it's just a couple lines of code, but I'll point out a highlight with that and see as well. All right, so I prototyped a couple of my methods here. So I have an initial call to MergeSort that just takes in an array, but then I have a MergeSort helper, a la our scheme class, right? That takes in that array as well as what the initial beginning and ending is, well, as well as which part of the array we're currently looking at. So this original call to MergeSort, all that guy does is call the helper, passing it 0 and actually, it's not a bug, but I've just hard coded a 9 in there. That guy. Make sure I didn't just break anything. Now we're good. All right, so it just calls MergeSort helper with the original beginning, which is 0, and the original end, which is whatever array size was -1, the last legal bucket. All right. So really our algorithms here inside of MergeSort helper. Okay. So up here in main, I go ahead, I give myself a time t type. So this guy is some kind of struct type of type time t. Actually, it's not going to be a struct type. It's just going to be a type. So probably an int, maybe actually might be a double. I don't know what actually type it is, but it's a something built into time.h that is used along with this sran function. So sran seeds a random number generator. Common problem, and certainly, well, this is something you have to consider with any programming language you look at. But a common computer science problem is true sources of randomness are actually difficult to come by. So even the best random number generator is maybe not as random as you really want it to be. If we're comparing it to randomness across all numbers or something like that, because it has to operate off of a lot of times in Unix systems, it pulls data from something called dev null, which just feeds it random data. It's picked up from like hard drive reads and writes and mouse movements and things like that, with the idea that, oh, well, that's probably random. But even among that, if you think about it, every time you move your mouse, it's picking up data. There's still some patterns to how you move your mouse. So is that truly random data? So it's kind of an interesting side discussion of what is truly random. But in any case, typically a random number generating function like this rand function here, it's going to operate off of some starting value. And if we always have the same starting value, as in we don't give it a seed value, it will always generate the same sequence of random numbers every single time you run the program. Java used to work this way. In the Java class, we typically will use the random object, random r equals new random. That guy we used to also need to seed, although they've updated it where it kind of self-seeds in whatever way Java's decided is the most appropriate way to seed the value. But in any case, what we're doing here is we're going to say, I'm going to go ahead and seed our random number generator with the current time. Usually this number is in milliseconds since 1970. It's called epoch time. EPOCH is what you'll a lot of times see it written as. But bottom line is, this is going to be some gigantic millisecond number that changes every millisecond. So presumably you're going to get a different set of random numbers every single time you run this. So that you aren't, it's actually a decent way of testing your code if you allow yourself to always get the same set of random numbers, because you can detect where there's bugs or something like that. So there is an advantage of having a random number generator that does give you a mixture of numbers, but always gives you the same mixture of numbers for testing. But in practice, if you're getting random numbers, you probably want to have it be really different numbers every single time you run it. All right, but whenever you see something where it's talking about seeding a random number generator, that's what it's doing. It's giving an initial starting point. So you just have to do this once, and now this program will generate different random numbers. All right, I don't remember, have we looked at malloc in here yet? All right, so this is going to be something that's going to be an important from creating an array perspective. And I actually do it the other way later on, so I'll bring awareness to it then. But I'll say it again here. We can create an array like this, or I can create that same array. Well, what's seemingly the same array that way. Now, most of us would look at this and say, this is better, right? Looks a lot more friendly. But while they're mostly equivalent, they actually are not identical. In this case, it would probably work because main is the last thing to die. But if you're inside of another function, and you create an array using this, what I usually would call this is something like syntactic sugar, kind of a shorthand syntax for it. What it's doing is it's creating very local memory that only is alive as long as this function is still alive, which means if you pass it to another function and you make changes there, those changes, it was actually kind of passed by value, not by pointer, because of the way this array is created. So I would say a good rule of thumb would be, it's okay to create arrays this way if you're only going to use it locally in the current function. If you're going to pass it to another function, you want to make sure you're dealing with an actual transferable pointer type. And that's what we're getting up here. All right, and we're going to see an example of this down below where I choose to use the other version of it along with the pointer that was passed in. So I'll reiterate it when we get down to it. All right, but malloc comes from standard library. And what malloc does is it memory allocates. This is equivalent to the new keyword in Java or C#. It goes and gets us some memory. How much memory do I want it to give us? Well, I have a macro up here called array size, just a constant value called size 10 I put here. You can make it whatever number you want. So this is going to say, I want to allocate some memory. And what you put in parentheses here is the number of bytes of memory you're requesting. Okay. So I want to get whatever array size is, and right now it's 10, times however big an integer is, because I want to get 10 integers. I want to get enough memory to hold 10 integers. All right. So this is the number of bytes I need. I want 10. I'm going to have 10 times size of an int is usually 32 bits or 4 bytes. Give me 40 bytes of memory. Make sense? So that's what malloc does, is it goes and retrieves stuff from the operating system. Same thing as our new keyword. By default, malloc returns a void pointer. That is a memory address that doesn't have a type associated with it. So I am typecasting that pointer. I'm saying, oh, you are actually an integer pointer. That's the kind of animal that I want you to be, rather than a void pointer, which comes out as. Why might I want to have why might I want to specify it's an int pointer instead of a void pointer? Where would this become a problem? Anybody know? I'll give you a hint on the next line. So let's say I said AR at bucket 3 is equal to, I don't know, let's put a value there. It's equal to 7. How would this behave differently if this was an int pointer versus a void pointer? What's actually happening when I say AR at bucket 3? What's happening under the hood? Go ahead.
You're pointing, you're selecting bucket 3.
How am I getting to bucket 3? Where does bucket 3 live? When we deal with arrays require what kind of memory? Contiguous memory. So memory right next to each other, right? That's how arrays work. That's why arrays are fast. Why do they require contiguous memory? What's actually happening under the hood when I say AR at bucket 3? Ultimately, I'm going to get to bucket 3 of the array, but how am I getting there? Go ahead.
You go to like wherever the array actually is. Does that make sense?
Yeah, so you start off by going to the base address. So the variable AR holds a memory address, right? It holds the place where that array starts in memory. And then you're going to take 3 steps forward through memory to get to another memory address, which is bucket 3, relative to the beginning of that array. So arrays need to be stored in contiguous memory so that works, right? We have to rely on all the things to be right next to each other. Go ahead.
It might not really matter. I'm just curious. Can you take 3 integer size steps and you can take 1?
That's exactly what we're talking about right here. If my array is an int pointer, C will, so effectively, I'm going to rewrite this. I'm going to write the same line a different way. I'm going to say AR plus 3, that value is equal to 7. These 2 lines accomplish the same thing. This is just doing pointer math. I'm saying, hey, start at the base address, add 3 to it, and then set the value at that address equal to 7. All right. So this line and this line do the identical thing. So his question, which is the correct question, is when I say plus 3, how far in memory am I actually going? Well, if AR is a integer pointer, C is smart enough to know that, oh, you want to take 3 integer size steps, 4 bytes at a time as you're stomping through memory. Make sense? If it's a void pointer, it's going to go down to the lowest common denominator, which is single byte size steps. So you're going to actually arrive 3/4 through the first integer, just picking up the next 4 bytes, but starting from that point in time. So you're going to get kind of a I don't know, a jumbled the jumbled offspring of part of bucket 0 along with part of bucket 1, most of bucket 1, I guess. Probably not the number we were looking for. All right. So it does matter whether this guy came out as a void pointer or if we cast it to an int pointer, because that then informs C later on when I use a syntax like this or like this, because these are equivalent. how big are each of those three steps as I'm walking through memory? Does that make some sense? So ultimately, this comes down to why are arrays stored in contiguous memory, just like they are in every other language. But because languages like C and C++ give us direct access to memory, if we're going to directly work with memory like we are right here, using malloc, which is the old school version of the new keyword, we have to know how big those steps are when we walk through memory, because it's just going to operate off the data that it has. And if it's an array of generics void, it's going to take 1 byte steps. Make sense? So that's why we're going to take that integer or that void pointer that's coming out of malloc and tell C, that guy, I want you to treat him as an int pointer. Okay, we're okay because we requested enough total memory. Malloc just goes and grabs some real estate. All right, how you choose to use that real estate is up to you. Make sense? And we've seen this. We've seen what probably is happening behind the scenes when we're allocating memory for our shared memory. We did something very similar. We say, hey, give me a pointer to shared memory that's this big. Make sense? All right. So this guy just dictates when you're walking through that memory through an array, how much work do you want to do yourself versus how much work do you want to do, C to do for you? If you said this, you had it as a void pointer and you wanted to walk through memory, you would have had to say, take 3 times size of int steps. That's how far I want you to jump into memory. Because if you treated this guy as a void pointer, it won't know that those are 4 byte steps. So instead, you would have to then inform C that each step is 4 bytes. I want you to take 3 of those, add that amount of memory onto the base address, and set the value there equal to 7. You can still pull it off if you just want to do a lot of pointer math, but you might as well take advantage of what C is going to give you and let it go ahead and walk through memory on its own. All right, that makes some sense. All right. So that's what we're doing here. We're allocating some memory. How much memory? This number of bytes. And then I'm going to store it. So effectively, we just defined an array. This line's equivalent in Java to int array AR is equal to a new int array of size, I don't know, array size, like that. That's the Java equivalent. Java seems a little friendlier. Keep in mind, though, that, and this is where things get a little sketch for new school programmers, people who do Java and C# and go back and write old C stuff. These two guys are not actually 100% identical because it's local memory only that's being stored contiguously as opposed to system level memory, which wouldn't be a problem probably most of the time. But depending on what you're doing with that array, it could be a problem when that memory address that was automatically requested for you inside of a function, when you do it like that, all of a sudden is reclaimed by the operating system when you didn't expect it to be. Okay. So good rule of thumb is in C, if you want memory, go ahead and allocate the memory. Don't use the shortcuts unless you know exactly why you're using the shortcut. All right, so create our array, seed our random number generator, go through and we're going to fill up our array with some random numbers. I'm filling up with random numbers between 0 and 20. Actually, this will be 0 and 19. because anything mod 20 will give me some number between 0 and 20 minus 1. All right, you could pick a different number here if you want to fill your random number, fill your array up with different random numbers, but this will get us what we kind of want, a jumble of numbers that are readable by us. All right. So now, just to kind of show, I just wrote a little display array function that takes in a pointer to an integer array and then how many elements are in there. There's one weakness of C. We say it's a weakness, but arrays in C they have no way of reporting their length like they do in Java. In Java would say AR.length. C, we can't do that. So my display array function I wrote, I'm just gonna pass in, here's the array. This is how many buckets are in it. Go ahead and display it for me. So that's all that guy does. Writes a loop, goes through all those things. Actually, array size is correct here for what I'm doing, but really you want it to make it generic. Put the length that was being passed in. And we're just going to print them all out one line at a time. So there's our random numbers between 0 and 19. If I run it again, we see we get a different set of numbers, so on and so forth. And just out of curiosity, I want to see how old this C compiler is here. If I don't see the random number generator, presumably I'm going to get the same collection of random numbers every single time. So same collection of random numbers every single time. Probably not what we want a majority of the time, but I could see examples of when that would be helpful. Yeah. Yeah, I believe so. I don't see any reason why. SRAND might be picky about the kind of value it takes because I'm not exactly sure what time t is. But it'll probably just tell me what time t is if I just throw a 1 in here and run it. Yeah, if I throw a 5 in there. Always getting the same numbers, whatever the seed value is. So it looks like it's automatically seeded with a 1 if you don't do anything special, is what we just kind of noticed there. All right, but they should give us a reasonable source of randomness since we're pulling our seed value out off of some millisecond number. All right. Now let's actually look at our MergeSort. Oh, one other thing I'll point out real quick though is up here, since we allocated this memory ourselves, it is now our official responsibility to free that memory while we're done, when we're done. Give it back to the operating system. Realistically, most modern operating systems will just take it back once this process dies, but good programming practice would indicate that you should clean up your own mess. Okay, so that's what that free is for down here. Right before the program ends, I go ahead and officially give it back to the operating system. So let's look at MergeSort. Like I already said, MergeSort just takes in our integer array and it calls MergeSort helper with the correct initial beginning and end. Bucket 0 and bucket 9 is what it will be initially. So really our MergeSort, based on what we just explained, is this guy right here, MergeSort helper. So this first part here says, is this portion of the array trivially sorted? If it's not a 1 list, we have work to do. If it is a 1 list, we're done, right? So if begin is something different than end, that means it's not a one list. So if it's not a one list, we have to determine the first half, the beginning and ending of the first half, and the beginning and ending of the second half. And then we call MergeSort helper on the first half, and we call MergeSort helper on the second half. Just like we depicted when we walked through this, right? So the beginning of the first half will always be equal to begin. This is the tricky part. So the ending of the first half, you might be tempted to say n divided by 2. And that will always work as long as you're dealing with the left half of your array. The second you get to the right half of your array, you're going to start getting some very weird results, because all of a sudden end is going to be before begin for a particular calls to MergeSort helper. So that's why we say end plus begin divided by 2. Initially, end is 9. 9 plus 0 divided by 2 will give me truncated a 4. That's the end of the first half. But let's assume that I was calling the second half. Let's say it was bucket 5 to bucket 9. 9 plus 5 is 14, divided by 2 is 7. That's the end of the first half of that second half. Does that make sense? So n plus begin divided by 2 is the magic math that makes sure that you are giving the correct ending to the portion of the array that you're dealing with. So when you're dealing with MergeSort, that's typically a place to pay attention to for your bug. All right, so begin and end of the first half, begin and end of the second half. The beginning of the second half is just one after your hard to get number. That part's easy. Okay. Call MergeSort in the first half, call MergeSort in the second half. Once you've returned from both of those, and you saw when we went through the pictures, we get down, oh, this is a one list, this is a one list, bounce back up. Now we need to do a merge. The part where we create our temporary array of the same size as the portion of the array we're currently dealing with, and start picking winners depending on, because we know the left half and the right half are sorted in and of themselves. So the size of my temporary array will be this number of buckets, n minus begin plus 1. So the very first call to this, when we had begin is 0, end is 9 in this current example, we'd have 9 minus 0, which is 9, plus 1 is 10. I'm going to need a 10 bucket array to pick the winners for my original 10 buckets. So I'm going to create this temporary array of the correct size. Now notice here that I'm using this other format for my temporary array, because it's only going to be used locally here in this function. I don't need it later on. It'll go ahead and get cleaned up automatically when this function dies. That doesn't mean you couldn't have just written it to use malloc and then free it yourself before it ended. They'll both accomplish the same thing. This would just be an appropriate place where you could use the syntactic sugar for creating an array, since no external entities are hoping to have access to that pointer. And where this really becomes sketch, if you wanted to create an example of this, let's assume at the end of this guy, this function, I returned the value of temp. So I created temp here, and let's say this function returned an int pointer. So it returned the value of temp. I might believe I'm giving it a pointer to real memory. But what it just did is at the end of that function, somebody else has a memory address that points to something that's no longer owned by this process, because it was cleaned up at the end of that function. Does that make sense? So if you need external access to this guy, make sure you're the one claiming the memory, so you also have control of when that memory gets freed up. That can sometimes be a difficult bug to track down as well, which is why maybe a good rule of thumb is to just always use malloc. Worst that happens is you forget to free the memory, and the operating system will take care of it for you. Also bad programming practice, but at least your code will work. As opposed to having dead pointers being passed around. And a lot of times the telltale sign, although we don't get it in online GDB, but if you're using a different C compiler, you'll get, when you have access to bad memory, what's the error you get with C when you access bad memory? Just plays on the screen. It's usually a segmentation fault. You'll see that phrase, segmentation fault. Pretty much means you tried to walk on memory that you don't own. All right. I'd say 95% of the time that's what your bug is. So that kind of should zero you in on what to go and look for. Just another trivia type thing. All right. So we create our temporary array. And this is related to the question you asked. Pos 1 is going to be the beginning of the left half. Pos 2 is going to be the beginning of the right half, the index of it. I know this is the number of elements. This is the number of races that we're going to run when we're comparing those values. I'm going to run temp length number of races. If both pos 1 and pos 2 are both currently legal values, then if the value at bucket pos 1 is less than the value at bucket pos 2, place the value at pos 1 in my temporary array, increment pos 1. Otherwise, place the value at bucket pos 2 in my temporary array, increment pos 2. Else if at least one of the values is currently illegal, it's off the end of its little subarray, it's half. We'll say, well, if pos 1 is currently still legal, if I'm in this else part of it, I know one of them is illegal. One of them is not pointing to a real place. So I'm saying if pos 1 is pointing to a real place, then pos 1 wins by default. Place the value of pos 1 in my array, my temp array, increment pos 1. Otherwise, pos 2 must have been the guy that was still legal. Place the value at pos 2 in my temporary array, increment pos 2. We'll do that logic temp length number of times, and when we're done, we will have filled up our temp array with the values in the correct order between buckets begin and end of my array, whichever portion of the array we're currently dealing with. Make sense? One last thing to do. Copy the values in temp back over into AR, where AR was allocated memory that will survive until we free it, even though temp's about to die. Right, so this is kind of an important part. Although it would never make sense for us not to do this, because even if temp did survive this, we still need AR to hold our original correct values. So we'll just keep track, because we might need two different counters here, right? We can't just always rely on AR being starting at bucket 0 and temp starting at bucket 0. Temp will always start at bucket 0. But as we're walking through the portion of our array that we're currently looking at, it actually begins at bucket begin, whatever begin is. If it was our original first call to merge sort, begin happens to be 0. But if it was our second original call, the right-hand half, begin in our current example would be 5, right? I'm replacing bucket 5 of AR with whatever's at bucket 0 in temp. That's why we have two separate counters here. Temp is always 0 indexed, and you could create temp inside this for loop. For loops support creating multiple values. I just made it outside of it. So go through all the elements of AR, set AR at bucket I equal to bucket temp pos of temp. Increment temp pos each time. So I'm just copying the values back over from temp. And then this call to merge sort helper ends. I've done my merge. I've completed sorting between bucket begin and bucket end in AR. whichever portion of AR I'm currently dealing with. All right, make some sense? All right, questions about that code? Hopefully those two things line up. This is the code version of what we described in pictures at the beginning. Okay. So now I'll pose the question. MergeSort was initially advertised to you when you first saw it as a more advanced sorting algorithm, right? Certainly it's more complicated, especially as a beginning programmer where you don't like recursion. Now, most of you have now had 470, so now you all love recursion. Recursion is not a big problem anymore, right? Well, you might not love it, but it's less of a problem at this point, right? All right, so maybe that double recursion thing is less of a freak out problem at this point, but tell me about recursion. Is recursion considered to be efficient? What happens when you make a function call, when you make a recursive function call? Recursion is when a function calls itself from within itself, right? Go ahead.
I don't think it's more efficient. I think it's probably the same, if not less efficient.
Okay. Good.
I feel like it's less efficient because when you call a process within a process, that other process is still running. So you have two processes.
Okay. We're going to be talking about that half of it here in a second. Remember, up to this point, all the ways you've always viewed MergeSort has always been within a single running process, right? So the sub question I'm asking here is when you have a program that's running and you make a recursive call, what happens to the current state of your program? Go ahead. Gets put on hold. And how do we put a function on hold? So if we say recursion is when a function calls itself from within itself, and we now make another recursive call. So like we did right here, when we made this from inside of MergeSort helper, when we made this call to MergeSort helper, what happened to the current call to MergeSort helper that we were working with? It gets put on hold, but how? Go ahead. Okay. If you're positing that the operating system will block the process? Potentially, right? Because at this point, it's only a single running process. This isn't multi-threaded or anything. It's a single running process. We can't have the operating system block the process because then this recursive call won't happen. Go ahead.
I would propose it would suspend the previous process.
We only have one process. So if we want this second call to MergeSort thing and similarly the third call, right? And whatever calls happen inside of that guy, we want these other calls to ever occur. You know, we can't hang this process. This process has to still be alive, okay? But we are going to pause the current call to this function. How does that actually happen? Go ahead. Well, okay, I think you are kicking the ball down in the right direction.
Could the process restart itself?
Okay, it doesn't, but we're in the right kind of maybe sort of zone here. Let's assume it does restart itself. Eventually, I need to get back to that original call, right? I need to be able to return to this code here where begin right here is the value of begin that was passed into this call to MergeSort helper, not something that happened from either of these calls. So when I come back to this function after those recursive calls have happened, I need to have my original values. Go ahead.
So to address that problem, could you store the previous values in memory before the recursive call?
We got to store them somewhere.
And then
Okay, we certainly got to store them somewhere. Remind me, what's a context switch as it relates to operating systems? Okay, so it deals with the operating system's management of the processor, right? So the CPU is easiest to discuss when we have a single core CPU where everybody's competing for this single resource, right? Modern operating systems that work from multi-core processors become more complex, but really the same thing's happening, but it's easier to discuss with a single core. So we have the single resource, a single CPU. And one of the jobs the operating system does is it tries to fake out the user, right? Which means it's going to do stuff really, 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 really fast, even though there might be 10 programs, 10 processes running on the operating system at that exact moment. It's going to give each of those 10 processes just a little bit of CPU time so that we believe, as the dumb people, that everything's happening simultaneously because it's happening so quickly. The context switch is what happens when a process is leaving the CPU and another process is coming on to the CPU, right? Now, if each time, now that doesn't mean that the process that's leaving the CPU is done. It just means it's run out of its allotted time, right? So maybe we give a process, we'll just use human measurements of time. Let's say each process gets 1 second of CPU time. It gets way less than that, but let's just assume it's 1 second, okay? If that program can't run to completion in that 1 second, but it's still getting kicked off the CPU, it's got to go get back in line waiting for the CPU again. But when it gets to the CPU again, does it start from scratch? Does it start over? No, it's got to pick up where it left off. But what does it mean for a process to pick up where it left off? So let's say I'm a process. I've already had my first use. I've been on the water slide once, right? And now I got to climb. I hate climbing back up the stairs at the water park. Wouldn't you pay extra for like an elevator? Totally would pay extra for an elevator. Even when I was a kid, I hated it. Like when I could still like do stairs, it was garbage. But I digress. So we've already had our run on the water slide. Now we're back in line, waiting for our next second on there. How do I know when I get access to the CPU again, where to pick up where I left off? What does it mean to pick up where I left off when we're actually running on the CPU?
I don't know if this is exactly correct. You could have like.
Is it going to be partially correct?
Partially.
I just teasing. Go ahead.
Like you could have like some sort of marker indication point of where the process picks up again.
That would be helpful,
Yeah.
right? Some sort of. This is something you did in 350. You would have talked about this in 350, right? You did context switching? Go ahead.
Oh, so is it when you're about to leave the CPU, you get a little sort of thing, saying like, this is what I want.
Okay.
You go off the CPU and then come back, the CPU and that here's where you go.
Okay, so this is where really 3 classes come together, right? So this is kind of Dr. Locklear's grand ideas of computer science. So this is where computer architecture, 325, meets operating systems, 350, meets 450 systems programming. When you compile a program, when you compile a C program, it turns into low-level code. We talked about that like the first week of this class, right? So that's going to be assembly code. Now, when you look at assembly code, a lot of the ninja moves that are happening in assembly code deals with putting values, moving values between memory and like hardware registers, right? What's a hardware register? Remind me about that. We're dealing with Intel-based assembly like AX, BX, CX. Go ahead.
Placed in the CPU.
Yeah.
Storage or like.
Yeah, little tiny bucket of memory inside the CPU. I like to think of it as basically a hardware variable. And the CPU does not have an unlimited number of those. Depending on your vintage of CPU, you have between, I don't know, let's call it maybe 10 hardware registers and I don't know, maybe 32, something like that, but definitely not thousands. And you got a couple of different types of memory you can use. You got the hardware registers, which are going to be super turbo fast. Then you got the L1 cache, L2 cache, L3 cache, and then you got system memory. right? And the closer you are to the CPU, the faster and more expensive per bit of memory you're going to be dealing with. But those hardware registers, those are attached to the CPU. And L1, L2 cache is also part of the CPU's, it's kind of in the backyard of the CPU. L3 cache is actually used across multiple processor type things. So it's shared between cores. But in any case, when I'm a program, and I've had them during my first 1 second running on the CPU, you know, I kind of stretched out, right? You know, I kind of threw some values into the different registers there. Maybe I put some crap over here in, you know, in cache, in L1 or L2 cache. Okay. All of a sudden the operating system say, hey, get out. You got to leave. Well, a couple minutes later, I'm going to be back here, picking up where I left off. So that means I need to remember the current state of all this stuff, right? I got to remember what line of code is my next line of code. So in assembly, it's called the program counter. You know, that's usually stored in one of our hardware registers, especially one for that. Then I have what are the current state of all those hardware registers where I've kind of temporarily stored some values in preparation, let's say, for the next line or the next several lines, which I haven't gotten to yet. Maybe I need to store the stuff that's currently in L1, L2 cache. But in any case, I need to remember all the current state of my world so that I can restore that state next time I get the CPU. Does that make sense? That's quite a bit of crap that I need to keep track of, right? You know, the way I like to think about it is kind of like when you go into a hotel room and you unpack your bags, right? You get there, you unpack your bags, start throwing stuff into the drawers, whatever, especially if you're going to be in a room for multiple days. You know, if you're just there overnight, you probably just live out of the suitcase. But whatever, let's just assume that we're unpacking, hanging stuff up in the closet, whatever. And then all of a sudden they come and say, get out. And you got to repack all your stuff up so that you can unpack it again when you get back to the room, something like that. That would be inefficient. That would tick us off, right? It's kind of the worst part of traveling. It's the packing and unpacking. So that whole process is called a context switch. The idea of having the process that's leaving the CPU pack up its stuff and having the process that's getting back onto the CPU unpack its stuff. That's a lot of extra stuff that's happening that isn't processing stuff, right? We're not making headway towards our logic. All we're doing is just unpacking bags and packing bags. So we would say that context switches are expensive. They're bad. We want to minimize context switches. Well, what's the easiest way to minimize context switches? Go ahead. Okay, and how do we avoid doing them? Okay, even having fewer processes, you'd still have context switches. How do you avoid? Let's just go with the extreme example. How do you avoid context switches entirely?
Don't do your homework.
How do we have zero context switches? How do we guarantee zero context switches? Go ahead. Okay, which means what? We're not quite the recursion yet, but it's probably a true statement. Go ahead. So it's done. Yeah, no more. Let's trick the human. Okay, you know, like, look, we're not going to do this stuff really fast. So you think everything's happening at once? No, one program is going to run at once, and it's going to run until it's done. And when it's done, then your next program, that's called batch processing, right? Well, you don't have context switches. Your programs will at least run as quickly as they can possibly run, depending on the number of instructions, number of millions of instructions or whatever it has. Zero context switches. Okay, but the problem with that is what? Ticked off users. Computer's too slow. I can't listen to my music at the same time as I'm checking my email. This is unacceptable. So we got to get that balance between number of context switches and the time that a process lives on the CPU. So one of the things you would have talked about in 350 is some various algorithms for how do we determine the amount of time that a process lives on the CPU. Kind of your most generic ones are like round robin, where you just give it a fixed amount of time, and then, you know, get out of Dodge. And that's kind of the example we just used, which everybody just gets 1 second or until they're done, right? If it takes less than a second, then we don't just make them hang out there until they're done. Well, they get out of Dodge. Another thing you do is with priorities, right? You might have some processes on the, you can still do round robin, but round robin with priority. So that's the Disney World idea, right? You go to Disney World and can't you buy like the Mickey pass or something that lets you cut the line? It's called Fast Pass. Yeah, you cut the line, but then the problem is everybody has Fast Pass. So you're in a second line for Fast Pass, just different lines, but you just spent more money. It's great.
I'm gonna say now it's called the Genie
The
Pass.
Genie Pass,
I think it's Genie.
that sounds made up.
No, it's actually, they changed their.
I think they text you like when it's your turn. It's kind of like making a reservation at a restaurant. They text you, yeah, come, you know, it's going to be about a 20-minute wait. Just come back, go have one of your $30 Mickey Mouse funnel cakes. See you in a few minutes. All right, so that would get rid of context switches entirely, right? But we can have priority and make sure that at least the most important processes get the CPU next. Different ways we can accomplish that whole CPU scheduling thing, but we certainly can't say that context switches can completely go away because the end user won't be happy. So all we can do is try to minimize them and find that balancing point between the correct number of context switches and the end user being happy that everything seems to be happening at once. So big smiles, right? So now we're back to the original question. How does recursion work? If we're dealing with one process here, right? Single process right now. If that process makes a recursive call, does that mean he gets kicked off the CPU, or is he still running? He's still running his code. Yeah, there's no context switch yet. He's still, whatever his time's up, he's done. But when he makes a recursive call, he has to put everything from the current call on hold. Sort of, kind of like a context switch, right? Except it's happening within the software. So what are the things that an individual running function needs to remember, similar to a process needs to remember about all the current hardware registers and the state of the cache and the current program counter, all that stuff? What are the things that a function needs to remember to be put on hold for it to call itself a different time with different values? Just to remember the current value of its parameters, right? All of its local variables. It needs to know what's the current value of I, current value of J, count, whatever variables it's created locally. It has to remember all that stuff so that it can restore its state when the recursive call, or in this case, the two recursive calls finally end. When both of those guys end, and we get back to this line right here, this guy, we need to now have our memory restored to what it was before so that we can keep going. The current value of begin when we get here is not the begin that those guys may have changed. It's the begin that I had a few minutes ago before I made those recursive calls. All right, so a function sort of kind of packs its bags and then throws itself onto what's called the system stack. All right, so we have this stack of, I don't know, function suitcases, if you will, that have the current state of a function stored in it so that when that function is the active function again, it can pick up where it left off. Make some sense? All right, so that's how recursive calls work. They're inefficient from a memory perspective because every single time we make a recursive call, we're having to build that suitcase, toss the suitcase on the stack of suitcases, waiting for us to come back later. And every single time we have to remember a bunch of stuff, that takes up memory, right? Okay. So recursion is considered to be memory inefficient. What's good about recursion? Nothing. I don't know why it exists. Okay, well, why is that good? Anything you can do recursively, you can do iteratively with a stack. You write your own stack, you can write a loop, and whenever you need to save something, just throw it on your stack. You're effectively implementing recursion yourself without it being recursion. But what's good about recursion? Is it? Recursive solutions relative to iterative solutions are usually shorter, right? A lot of times we see the result is more compact. Something we might say is oh, the solution's more elegant, okay? Or when you're an inexperienced programmer, you might say the solution is more impossible to follow. You know, that's what happens early on because your mind gets into these knots as it's making these recursive calls. And MergeSort is the king of that because now you have two recursive calls where everything just goes, right? Recursion is not fast. Recursion is not memory efficient. So why recursion? And to our point here, why MergeSort? If recursion's not fast or memory efficient to begin with, double recursion would be bad. When does MergeSort shine? In what situation is MergeSort actually a fast, efficient sorting algorithm? Go ahead.
When you have multiple processes.
Oh, yes. When you have multiple processes that can potentially run on multiple CPUs, or prior to us having multi-core CPUs or multiple physical CPUs, having some sort of network-based message passing interface that allows you to offset some of, hand off some of your workload to other computers, physical computers, effectively distributed computing. Okay. So the idea here is, when we go back to our MergeSort here, we start calling our original MergeSort. Forget about the fact that it's already sorted right now. Not all that important for what I'm about to talk about. So you're looking at your current MergeSort. You say, is this, so I'm the original parent. I say, well, is my stuff sorted? Well, begin and end, not the same thing. So what am I going to do? I'm going to create a child to sort that half. I'll create another child to sort that half. And then what is the parent going to do? When can the parent start doing work again? When can this parent that I have highlighted, when can they do their merge step?
When the two of the processes that broke up are done with their processes.
Yeah.
And I guess when they break off, they have to wait for each other.
So this parent will wait for this process ID to finish and for this process ID to finish. Because once they're finished, then the parent knows that they can do their stuff, right? Similarly, this guy will become the parent of two child processes. And he has to wait for both of these processes to finish. Now, we still are picking up speed because if we're on a multi-core system, it's potentially possible that this process and this process are running simultaneously on different cores of the processor. Actually running at the same time. Make sense? Even though this guy cannot continue until both of these sub-processes have finished. All right, make some sense? Similarly, this original call this guy can be running at the same time as this guy is running. So we're not waiting for the entire left half to be sorted before we even start on the right half. We could have both of those guys off to the races, working at whatever pace they have to work in order to get the job accomplished. Make sense? All right, so what we want to do I'm going to say given, just make sure this guy. So there's our working merge sort. Okay, so I'll save this. And what I already gave you online works, but I didn't have a couple of global variables popped in there, but it still works for the current thing. So given that, update our recursive version of MergeSort to operate with multiple processes, which potentially work, well, handle both sides of an array at the same time. So some hints here. Our memory, our array, probably needs to live in shared memory, right? All those processes need to have access to that guy, even though they might only be working on a little portion of it. Make sense? All right, so you have a recursive version of MergeSort. Now you're going to write a multi-process version of MergeSort using only what we've learned in class so far. So you have your inter-process communication tools that we've dealt with. Make sense? Should be easy. It actually won't be that bad. It's probably easier than writing MergeSort normally. All right, questions, comments, concerns, bribes. All right, I'll see everybody on Thursday. Yep. Next semester. 250 this semester. No. 300s in the
I
fall.
just need a message to this live chat for this channel and
Yep.
for the hack.
Yep.
Just wanted to make sure it was
Yep.
a message because I want to make sure everyone knows that they need to go to that. Has to